So today we'll be talking about diffusion and velocity. So this is your lecture for Friday, June 5th. So we are kind of like a day ahead, but I have something else planned for the rest of our time, and I will talk a little bit about that with you guys tomorrow during our meeting. So this again is for Friday's lecture, June 5th, and we're going to have a check-in tomorrow at 11, and then we will also be having our class lecture, kind of going over questions and different things on Monday. So we'll talk a little bit more what the rest of the science part's going to look like. Okay, so diffusion and velocity. So again, more terms and a few more laws. So hence why your science plan is going to be open book, because there's so much material. Alright, so diffusion basically is a process where molecules are moving from one area of high concentration to an area of low concentration. Okay, that's just kind of the nature of that. So when something diffuses, it's going from a high area of high concentration to low concentration. So it's a slow, steady movement of individual molecules from one region to another. And the kinetic energy then is that driving force behind the diffusion. Gases have a high kinetic energy, so they diffuse more rapidly compared to liquids and solids. Okay, so we're mainly dealing with gases as respiratory therapists. But when we're comparing the different states of matter, solid, liquid, gases, gases have the highest kinetic energy. All right, so when we're looking at diffusion, we are concerned, or wanting to know how well gas diffusion is happening. How well is the oxygen being able to diffuse across the alveolar capillary membrane from the air to the lungs to the blood? Okay, so gas diffusion then takes place in the lungs, and then the oxygen and the carbon dioxide have to move through different barriers, mainly the alveolar capillary membrane. And so the lung tissue, which is composed of the alveolar epithelium, and that's kind of where it's at the gas stage, where the O2 is, and then mainly the capillary wall, which is the capillary endothelium, the plasma or the interstitial space, and then the membrane of the red blood cell, which is hemoglobin. That's mostly water, or mostly liquid, which consists of mostly water. So when you're looking at the different barriers through the alveolar capillary membrane, you want to remember then lung tissue, capillary wall, plasma, and then the membrane of the red blood cell, or hemoglobin. Alright, so we have different laws, again, that affect that diffusion. We have Fick's law, Graham's, and Henry's law. And these are actually also explained in your Egan's textbook, like page 250s, like 254 is one of them. And then it's also explained in Desjardins, which unfortunately I don't think you guys have yet. Alright, so we're looking at Fick's law. Okay, Fick's law involves the surface area, a diffusion constant, a pressure gradient. Okay, so the greater, so we're looking at different things. We're looking at area, the diffusion constant, and then that change in pressure, or the pressure gradient, all divided by the thickness of the tissue. Okay, so according to Fick's law, the greater the surface area, then the diffusion constant and the pressure gradient, the more diffusion occurs. So as opposite, the greater the distance across the membrane, so if the membrane is thicker, less diffusion occurs. So just kind of thinking of how we would kind of look at that. So if we look at those different variables there, the A, D, change in P and T, some different things just to kind of think about. When we think of area, cross-sectional area, we think of the larger area. So things that would affect our lungs having a decreased A or a decreased surface area would be alveolar collapse. So like with atelectasis, so if your airways are collapsed for some reason, your surgery, a post-op patient, not taking as deep of a breath, which also can be part of the pressure gradient, but areas of collapse, a pneumonia, anything that would actually compress on the lungs or compress on the capillaries can actually compress the airways. Or if we have fluid, like in pulmonary edema. So those conditions, alveolar collapse and alveolar fluid, are going to decrease the surface area. So that is going to lead to the decreased ability of oxygen to enter the pulmonary capillary blood flow. Okay. Another place that we would see, so diffusion constant then, that kind of has to do with a lighter molecular weight, and we'll talk about diffusion constant here coming up. P1 to P2, okay, so that's the pressure gradient. So we're going to see a decreased pressure gradient at a higher elevation or a higher altitude because we have a less barometric pressure. So there's less of a gradient. So the greater the gradient, will be the greater the flow, basically. Okay. Or hypoventilation. You're not taking as deep of a breath, so you're not having as much of a pressure gradient. Okay. So hold on one second. So if you have a greater pressure difference, you have more molecules diffusing. Okay, so greater pressure gradient or greater pressure difference is good. You have more molecules diffusing. And then when we look at the thickness of the tissue, that's kind of where we're looking at where would the tissue be inflamed. Things that would cause it to be inflamed, like a pneumonia, an infection, asthma, edema, inflammation, alveolar fibrosis. You have a buildup of scar tissue. Those are all going to affect your diffusion of how well the gas is going to get through, or the oxygen. Okay, so Fick's law then, the greater the surface area, diffusion constant, and pressure gradient, the more diffusion will occur. So you have two videos here to watch, which will hopefully help explain. The first video link is about 12 minutes, and I have a little note to myself to go ahead and stop at 10 minutes, because then it gets kind of far out there where things that you really don't need to concern yourself with. And then the second one is actually really quite good. It has to do with oxygen movement from the alveoli to the capillaries. And that one's about, again, close to 12 minutes. So those are both really helpful videos, hoping to explain this concept of Fick's law. All right, so Henry's law. Henry's law talks about the amount of gas that dissolves in a liquid at a given temperature is proportional to that partial pressure of the gas. So the amount of gas then that is dissolved in 1 mil of a given liquid at standard temperature, pressure dry, is known as its solubility coefficient. Okay, so how well it dissolves. So the solubility coefficient is actually something that's a lab determined value, and just so that you know, the solubility coefficient here in water, so we're looking at comparing oxygen and carbon dioxide of mils per millimeters of mercury in mils of water, that in the CO2, carbon dioxide, is 26 times more soluble than oxygen in water. Okay. It also, carbon dioxide also diffuses approximately 20 times faster across the alveolar capillary membrane than oxygen because of its higher solubility in the plasma. Okay, so you want to know that's just a number you want to make sure that you know, that CO2 diffuses approximately 20 times faster across the alveolar capillary membrane. Okay, and so just kind of an example, and this is also talked about in page 117 in Egan. So gases can dissolve in liquids. So if we look at carbonated water and soda are really good examples to look at, and we can then see the example of gas of CO2 that's dissolved in the liquid or water. So Henry's law states that at a constant temperature, the amount of a given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. So we also look at how temperature can play a major role in gas solubility. So the higher the temperature, high temperature actually decreases your solubility, and low temperature increases the solubility. So when you look at a can of soda that has been left open, it still has fizz or carbonation when it's in the refrigerator, and it goes flat at room temperature. So low temperature increases the solubility, so you have more of that CO2, but high temperature decreases it. So the effect of temperature on solubility is related to the changes in the kinetic energy. So the effect of temperature on solubility is a result, again, of the changes in the kinetic energy. As a liquid is warmed, the kinetic energy of any dissolved gas molecules is increased. This is the increase in kinetic energy increases the escaping tendency of the molecules in the partial pressure. So it's related to temperature. Now, there is luckily another video here coming up to help explain Henry's law, but I kind of want to talk a little bit about when we're looking at oxygen dissolved in the plasma. So by applying Henry's law to oxygen transport, the amount of oxygen that's actually dissolved in the blood at 37 degrees, which is 98.6 degrees Fahrenheit, can actually be computed with taking the PO2, so whatever our PO2 is, let's say it's 80, and then we times that by 0.003. Okay, so a small amount of our oxygen is actually dissolved in the plasma. It's the smaller amount of the two, because we'll do another calculation coming down the road where you look at, because you guys haven't looked at that one yet, no. We did the alveolar air equation, where you look at how much oxygen content, it's oxygen content, and you look at the PaO2, and then you also look at the hemoglobin. And so the PaO2 you dissolve, or the PO2 you go ahead and just multiply that, the amount that is dissolved in the plasma is much smaller. So it's at times 0.003, which ends up being mils per deciliter. Compared to hemoglobin, we take that value, so your hemoglobin, let's say, is like 14, and you take that value and you times it by a constant of 1.34, and then so that number obviously is bigger than timesing it by 0.003, so most of your oxygen is actually carried by hemoglobin, but we'll go over that down the road here pretty soon. Actually, in pulmonary EMP, I'm sure you'll definitely go over this. Alright, so here is a helpful video for you. This has to do with oxygen and carbon dioxide solubility. This is a con video. and it is a very good video. I'm going to say it's about 7 minutes long. So definitely watch these videos because they'll definitely get the message across, because they draw all sorts of pictures and make a lot more sense than trying to read all this and understand it and listen to me. All right, Graham's law. Now Graham's law then states that the rate of diffusion of a gas through a liquid is directly proportional to the solubility coefficient of the gas and indirectly proportional to the square root of the gram molecular weight of the gas. Okay, so again, it's another lovely equation, but just kind of get the gist of how really, if you look at Graham's law, it's kind of like combining, you're looking at the diffusion constant. Okay, so your diffusion constant is equal to your solubility divided by your gram molecular weight. Okay, and your solubility has to do with Henry's law, which has to do with pressure, and your square root, that's your square root of your gram molecular weight, and that's Graham's law, which has to do with the weight of the molecules then. So lighter gases then diffuse rapidly, where heavier gases diffuse more slowly. So that kind of makes sense. So if you have a lighter weight gas, something like helium, which has a low molecular weight, compared to oxygen, helium diffuses more rapidly. Okay, so that's Graham's law. And again, because diffusion is based on kinetic energy, anything that increases molecular weight, or I'm sorry, increases molecular activity, okay, so speeds up those molecules moving around, such as heat, mechanical agitation such as pressure, that is going to speed up your diffusion. Okay, so you think about heating up a gas and then pressurizing it, you're going to increase that diffusion. And you have another, hopefully, helpful video to help explain all this. Okay, so that video should be helpful. Now here's just a little bit of terminology again. We're looking at diffusion percent effusion. Okay, your topic here is diffusion and effusion. So when I look at diffusion, which is demonstrated there in the top, that's the rate of this movement, or diffusion, is a function of temperature, viscosity of the medium, and the size of the mass of the particles. Diffusion results in the gradual mixing of materials, and eventually it forms a homogeneous mixture. So your diffusion here again is going from a high concentration to a low concentration. Okay, so you're looking at the top two boxes there. And then effusion then is explained by a continuous random motion of particles. Over time, this random motion guarantees that some particles will eventually pass through that small little hole. So that again is from movement of gases more from a high pressure to a low pressure. Okay, so if you're kind of just defining the difference of terms. So just know the definition of those two compared to each other, I guess, is the best thing to explain for that. All right, moving on to a couple other terms, flow and velocity. So flow you'll hear a lot of. That's actually part of how we look at how a gas is delivered based on the flow rate. It's actually something that we can manipulate on our ventilators. So flow then is the movement of volume of fluid per unit of time, is the technical, I guess, term. And it's in liters per second or liters per minute, depending on what you're working with. And then velocity is a measure of linear distance traveled by the fluid per unit of time, and that's in meters per second or centimeters per second. So Bernoulli's principle is kind of one of our oxygen delivery devices. Kind of has to do with Bernoulli's principle. It applies Bernoulli's principle, and I'll talk about that here in just on the next slide. But this might be something you've heard maybe back when you took science in high school. But so Bernoulli's principle is the increase in velocity is because the same number of molecules are trying to get through a narrow opening in a given amount of time. Okay, so that's Bernoulli's principle. So what happens is the molecules hit the side of the tube less often, therefore there is a drop in the lateral pressure. So the molecules then, based on Bernoulli's principle, are spending more time going forward, going faster forward, and less time hitting the walls of the tube. Okay, and this also has to do with jet ventilation too. So this drop in lateral pressure causes like a vacuum or a suction action that can actually entrain or bring in additional fluid or air. Okay. I know you're like, what the heck are you talking about? I'll try to explain here in the next few slides. So you get this Venturi effect, and that basically applies the Bernoulli's principle to allow fluid that flows through a tube with a constriction in it. And as this fluid flows through the constriction, the fluid molecules speed up. So kind of like thinking of like when you're partially blocking off a hose, when you're trying to spray like a hose. So you have a end of a hose, you have it turned down and the water's coming out. But then if you apply a constriction with your thumb and you kind of block it off, then you can spray somebody with it, or you know, the dogs or whoever, or wash your car or whatever, and then that's kind of applying that Venturi effect. Okay, so then it sprays out harder. So on this next picture here, this is a Venturi mask. They also call it an entrainment, E-N-T-R-A-I-N, entrainment mask, mainly because you're also entraining, you're bringing in room air. Now I know it's really hard to see here on these pictures here, but these are different adapters that you can switch out from the bottom of this mask. So you see the mask itself with this clear piece of tubing, and then on the bottom you have a green piece. Well, all these that green piece can come off, and you can switch it to the red one, to the yellow one, to the orange, the white, and the light blue. Now each one of these has different numbers on them, and depending on the size of the some of them have a different size orifice inside that you can't see, that are like pinpoint or narrower or wider, and then they also have a dial on the outside here. Most of them anymore don't have these interchangeable pieces. Thank goodness, or people would be losing them all the time. I'm sure that's why they got rid of them. But now we have a actual like adjustment. It can actually like turn, and as it turns, it's notched, and it gets like smaller or bigger. And that's the entrainment part here, where you can kind of see like the little adapter, the narrow part, and then you can see kind of right below the numbers, the different size openings. Kind of hard to compare them here against a flat surface, but three-dimensionally you can see it a lot better. So basically, the higher the amount of oxygen, the higher room air that you're bringing in from the atmosphere, you're diluting your oxygen amount. But these are still considered high flow systems because of the way that the oxygen is bled in through those small little orifices in the bottom of these little adapters. Believe me, we'll go over this more. This is kind of poor, but you'll be able to see it. There is a little YouTube video on this one here. So basically, the Venturi is a modification of the Bernoulli's principle. So as the Venturi tube widens just after the jet port, so that's what happens. The Venturi tube widens just after the jet port, and it depends again which size you have on here. So this helps keep the oxygen more constant by keeping that pressure and flow, so that there's not as much fluctuation that might vary on somebody's inspiratory demand. So that's why they call it a high flow system. So you think about somebody who's breathing really fast and deep, and they're kind of air hungry, they're going to be pulling more air. And this type of system, a high flow system or entrainment mask, can actually keep up with their oxygen demand versus just a low flow system at just running like at 2 or 3 liters. That's not enough flow. So we don't really, unfortunately, we really don't use these types of masks that much anymore. Back in the day when I first started, we used them quite a bit, and they do refer to them quite a bit on your boards. Of course, they call it an entrainment mask, but you can set it at a specific oxygen setting. So you can set them at like 40% or 50%, 30%, 36%, and it's pretty much guaranteed to deliver that amount of oxygen. So then again, the smaller the orifice, the greater the velocity of oxygen, and then more air is entrained. So you're still going to have a small amount of FiO2, your oxygen percentage might be 28% or 30%, but it's being carried by a lot of air, so it doesn't necessarily dilute it out because of the way that Venturi is set up. So hopefully that YouTube video can explain that also for you and help you out. And plus, when we get it back on campus, you'll get to see the difference of them and all the different adapters and the ones that we use, the style that we use more so now versus the different colors, and hopefully it'll make a little bit more sense. Plus, you also go over it in therapeutics, one with different oxygen delivery devices. Okay, we'll talk soon.